welcome to this public lecture. I'll begin with our traditional acknowledgement of country. I acknowledge the traditional owners of the land in which this event is taking place, the land of the Wurundjeri, and pay respect to their elders and families past and present. I'd like to introduce Professor Michael Brear to you. Michael is a professor of mechanical engineering, my department, and the Melbourne School of Engineering. Prior to taking up his position at the University of Melbourne, he worked for ICI Australia, now Orica. Then he undertook graduate studies at the University of Cambridge and postdoctoral research at the Massachusetts Institute of Technology. Michael works in transport and power generation, with a particular focus on low-emission technologies and alternative fuels. This involves close collaboration with the Ford Motor Company through ACART, the Australian energy market operator AEMO, Princeton University, the University of New South Wales, and others. He is also the coordinator of the university's Master of Energy Systems, which is a multidisciplinary degree that examines the technology and business of energy. The research that you will hear about tonight is supported in part by the Australian Renewable Energy Agency and the Melbourne Energy Institute. The lecture will be recorded and available for you on the web afterwards, and we will also have a few minutes for questions and answers, and that section won't be recorded. So it's my real pleasure to introduce Professor Michael Brear to you all.
Well, thank you very much, Professor Thomas. Doreen, my boss, Head of Department of Mechanical Engineering and Acting Dean for this evening. Thank you all for coming along tonight. I'm going to talk to you about decarbonising Australian electricity policy and technology options. And you say, well, this mechanical engineer might know more about the technology than the policy, and I wouldn't disagree with you, but I'll give it a crack anyway. All right, so before I start, I want to acknowledge a few organisations and a few specific people. Doreen mentioned the funding of this work is done by, performed by the Australian Renewable Energy Agency, ARENA, and also the Melbourne Energy Institute, which has been a terrific form of support. I would like to thank the co-authors of the work that I'm presenting here tonight, Dr. Matthew Jefferson, Dr. Deb Chattopadhyay, Professor Chris Manzi, Dr. Roger Dargaville, and Dr. Tansu Alpchan. I'd particularly, as you see, the first name in bold, Matthew is a research fellow who works with me. He did all the hard work and oh, that's not me, thank God. He did all the hard work and I'm presenting it here tonight, so I hope I do it justice. I was lucky enough for the second half of last year to go on sabbatical. It's tough being an academic and going off to the beautiful leafy state of New Jersey for 6 months with my family, where I could clear the diary, do some thinking, hopefully, and meet some interesting people who were working on similar problems over in the United States. I would also like to acknowledge my colleagues in engineering, particularly my department, the Department of Mechanical Engineering, but colleagues outside. Dr. Alpchan is from electrical engineering, Dr. Chattopadhyay was in electrical engineering, and Dr. Roger Dargaville is, we'd like him to be in engineering, but he's actually in earth sciences over the other side of the campus. Now, most importantly, I would like to thank people who've taught me a great deal over the years. My family, number one. Number two, it's the secret of academia. We always say if you want to learn something properly, teach it. So when you're forced to talk to bright young people who work very, very hard for not much money, they actually end up teaching you a great deal, and that's no different in this case. I'm very grateful for that. My students doing the Master of Energy Systems, which is a real honour to teach those students, and also my research students, the Masters and PhD students, who really are tremendously inspiring. And finally, if you wish to pronounce, as I will be tonight, on how the world should operate or might operate, it's a good idea to talk to people who operate the world and who design the world. And the more you talk to them, the more you learn. And so with that in mind, the learning I get from working with Ford in Australia, in Dearborn, in Detroit, and also in Europe now increasingly, is tremendously beneficial to our research group here at the university. Similarly, the work we've been doing with the Australian Energy Market Operator, AEMO, and a very good friend of mine, Mr. Tony Kitchener, who's here tonight. And finally, a small consultancy down in the city by the name of Market Reform, one of whom is here tonight. These people really have taught us as a group in engineering and a group across the university a great deal, and I really do need to acknowledge their support. So, before we start talking about decarbonisation of anything, we should define what is the thing we're actually decarbonising. So in this case, we're looking at Australian electricity, and apologies to anybody here from the Northern Territory or Western Australia, because I will be talking sincerely. This is a classic Eastern Seaboard thing to do. We're going to talk about the national electricity market, which is the wholesale electricity market that joins up the Eastern Seaboard states and South Australia. So Queensland, New South Wales, the ACT for market purposes is buried within New South Wales now, Victoria, Tasmania and South Australia. So the NEM, as I say here, is a wholesale electricity market that joins up consumers and generators across those states. The NEM, which is operated by the Australian Energy Market Operator, the NEM sets the prices and quantities of the electricity exchange between generators and retailers. And then the retailers act on our behalf in engaging with those generators to buy the electricity, which they subsequently pass on to our homes and our businesses. Now, when you're doing this enormous exchange of prices and quantities of electricity, the fundamental microeconomics is what's called a network market problem, where the physical performance of the network has a dramatic effect on what quantities of electricity can be bought and sold between states, within states of the NEM. I apologise, I expect I'll inadvertently switch between using the word state and NEM region because they're the same thing in the national electricity market. But it's the transmission network, the big poles and wires, from Loy Yang or Hazelwood into the city. That's the transmission network. But also the distribution network, which is stuff around our cities, which has a big say in what can flow where and therefore what prices are set throughout the system. And the chart on the right here is just a snapshot from a very well-known piece of software that people in the industry use a lot. And you can see a whole bunch of prices and a whole bunch of powers on it. So if you look at Queensland up in the top there, you can see $33. Well, that's the current, what's called spot market price in the NEM region of Queensland, and it's $33 a megawatt hour at that particular instant, as you can see on Friday the 8th of June in 2012 at 2:20 p.m. And at that time, 5,800 megawatts of electricity was being consumed. And that happens, AEMO is running this massive optimisation. It's an online auction, if you like, every 5 minutes, and settling these prices and these quantities of electricity. So quite a remarkable feat of microeconomic and technical analysis. And it's done in other countries around the world. There's several of these such markets run in the United States, and many other countries. A key thing to remember as well is when we are buying and selling this electricity, it's not just energy that we're buying and selling. So an energy is we could express that as in kilowatt hours, or we could express that in joules. But electricity as we buy it and sell it is more than that. Electricity that we buy and sell is a form of energy that has certain technical specifications, that is a quality, if you like. So if you're down at the Vic market and you want to buy bananas, well, the bananas have to have certain technical characteristics to be classified a banana to therefore be allowed to be sold at the Victoria market. Well, similarly here, the electricity that's bought and sold across the NEM has to have a certain frequency, it should be at a certain voltage, and it should be at a certain power factor. And you know that when you go home and you look at your power point on your wall, you'll see 240 volts AC, 50 hertz, okay? Now, it's that technical nature of this, in this case, alternating current electricity, that when people are talking about how to clean up the electricity grid, they underappreciate that often. And it puts quite acute constraints on what you can and can't do physically. Ooh, Sorry, wrong button. All right, so that's the NEM, and now we're going to talk about decarbonisation of the NEM. So what's the decarbonisation or the abatement challenge in front of us? So we're trying to make it here very straightforward. The modelling that Matthew and others have done in this work is quite a lot of maths. I'm not going to bore you with all that tonight, but we're just going to try and keep things as straightforward as we possibly can. So here we are. This is on the y-axis is the mass of CO2 that's emitted, the millions of tonnes of CO2 that's emitted by the national electricity market each year. And you can see in 2000 it was roughly a little bit above 160 megatonnes. This year it's up around the mid-170s. That's where we are today, okay? Now the question is where do we want to get to? Well, as a mechanical engineer, as an engineer, that's not a question which I can be involved in, but ultimately those kinds of questions are determined by the people who understand the risks and the damages of human-induced climate change, so the climate scientists, economists, and so on and so forth. So really, we're going to model tonight, therefore, a range of potential targets, and we're going to take 2050 as our year because that's the one that many people seem to be talking about at the moment. And just because we're engineers and we like keeping things as simple as we possibly can, we're going to say, well, we're here today, right now, we're producing about 170-something megatons of CO2 in the NEM today, and let's assume we want to get from here in a straight line to some point in the future. And that could be from 20% abatement by 2000 levels, which is what that red line is, all the way through to a zero-emission NEM by 2050. You'll see the dashed line in there as well, midway at 2030. I put that line in there just to highlight where a lot of the discussion's going on out in the community at the moment, and that's, of course, in the lead up to the Paris negotiations, and our current government has announced that the target's going to be for the Australian economy, so not just all Australian electricity emissions, and not just the NEM, including Western Australia and Northern Territory, but other sectors as well. For the Australian economy, they want to achieve 26 to 28% absolute abatement of 2005 levels. You always got to watch what year it starts from, by 2030. And the opposition at the moment says by 2030 we would like to have 50% renewables. Now, if we were to put that on this graph, and that's a big if, because there might be other sectors that achieve abatement more cheaply than electricity, and many people say that. I'm not sure if I agree with that in practice, but that's what some people say. You'd be sitting around about here for a government target with a very crude approximation, and then you'd be sitting down around here with that 50% renewables target, roughly speaking, okay? But there's no reason why we have to have a straight line abatement from now to any time in the future, and other agencies are doing different ways of modelling that trajectory, and they're perfectly valid. Important to note, nonetheless, that roughly a third of Australia's greenhouse gas emissions comes from electricity. So if we have a zero-emission NEM and we do nothing about anything else, and the rest of the economy stays static, we've only reduced our total emissions by a third. And that's an important thing to remember. So do we want to be zero emissions if the costs of doing that in this network means that we incur so much extra cost that we could have actually achieved more in other sectors with that expense or less? All right, so current generation in the NEM. No surprises. We all pretty well know, it's commonly known in Australia that we have a lot of coal-fired power. And we're not particularly unusual in that. We don't have nukes here, so compared to many other high-income countries, off the top of my head, most of them seem to have a fair bit of nuclear power generation, but coal is a dominant generator in many economies around the world. So let's compare what we currently have in the NEM, which is coal plant, natural gas plant, and varying forms of renewable plant, by 4 metrics that are important. And the first two, many of you will have already thought about a lot, which is the cost and the emissions. No surprises there. We don't want to do expensive stuff and we want to do clean stuff. But I'm going to introduce 2 more, and that's one's called dispatchability, or whether a plant is dispatchable, and another one is whether or not that plant provides inertia. And the question around dispatchability and inertia are technicals. This goes back to that technical requirement. It's not just kilowatt hours, it's kilowatt hours at 50 hertz and 240 volts AC coming into your home. okay, and with good power factor and hopefully not much harmonic content, blah, 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 things that engineers find exciting. Now, dispatchability, what does that mean? That means when the independent market operator, AEMO in this case, says to a power station, I would like you to turn off, turn on, produce more power or produce less power, the plant does that, okay? That is, it can be dispatched by the market operator. So AEMO works out who should generate what amount of electricity subject to the physical constraints to minimise the cost of electricity to consumers subject to certain reliability constraints, and then it dispatches everybody to take part in that orchestrated dance that's happening every 5 minutes, 24/7. Now, so dispatchability is a desirable thing if you're a generator in the NEM. Having inertia is a desirable thing if you're a generator in the NEM, because that's how we maintain having an inertia, this 50 hertz alternating current signal. Now, we get a spinning top when we were kids, we get a spinning top, we spin it, and that thing spins and for a while and then it stops and falls over. Or a bicycle tyre, when we spin that around and lift it off the ground, that has a moment of inertia and it's spinning around. Well, a turbine in a coal-fired power station or in other power stations connect to electrical generators, they also have inertia, and it's that inertia, that rotating mass that's spinning at 50 hertz or some multiple of it, that allows that whole system to be maintained at 50 hertz alternating current from the northern part of Queensland through to Hobart, through to South Australia. The whole system will be disturbed, it gets disturbed, it fluctuates in frequency around 50 hertz, but inertia is the physical mechanism by which that is achieved, and is therefore a valuable thing if a generator can happen to provide it. So what do we get? Well, coal, if we ignore the environmental externalities of coal, and that's an area of substantial investigation, let's at the moment just talk about the actual money of burning coal in the power station. Well, no surprises, coal's cheap, so it gets a tick for being cheap. Its emissions, coal doesn't get a tick for its emissions because it's the main thing that we actually want to do less of if we're wanting to achieve deep decarbonisation. So, for example, a typical coal-fired power station might produce about 1 kilogram of CO2 per kilowatt hour of electricity produced, or a tonne per megawatt hour, right? And that's roughly speaking the emissions intensity of our whole grid, because our grid is very coal heavy. Coal plant's dispatchable and it has inertia. So there's those other two features which are attractive in coal generation. What about natural gas? Cost? Well, a few years ago, 5 to 10 years ago, you would have given it a tick in Australia. In the United States, they give it a dirty big tick at the moment because natural gas is very cheap there. But in Australia, natural gas is getting more expensive, so you can't really give it a tick now. And in fact, it's really suffering a lot of natural gas plants in the NEM today. So we'll give that a hyphen. It's not too bad, but it's not too good either. Emissions, well, it's not as high emission as coal plant, but it's not zero emissions either, so it's in between the two. The most advanced or the most low emission gas-fired power station is what's called a combined cycle power station, and they're 50-ish, 50 to 60% lower emission than an equivalent coal plant. Not zero, but still pretty good. Dispatchability and inertia are features nonetheless. Then finally, for renewables, the short answer is it depends on what renewable you're looking at. So some renewable plants, even without any subsidy, like a renewable energy certificate or a carbon price, but some renewable plants already are cheap and will dispatch and be economically dispatched against coal and gas. No problems. The one in Australia that's done that for a long time is hydro, the Snowy Hydro scheme. Some are not as cheap. Some are more expensive. The emissions, well, they're a renewable plant, right? So they are clean, that's why we use them. Then similarly, dispatchability and inertia, it depends on which technology you're looking at. So in Australia at the moment, we have wind, we have solar, we have biomass, we have hydro, and hydro and biomass are dispatchable, do have inertia, and can be of low cost. But if we ignore the subsidies of all renewables, we would say that wind and solar are significantly more expensive, and they certainly do not provide inertia, nor are they currently dispatchable. Now, we can do the same kind of analysis for any future technology that we might choose to put into Australia, including nuclear, carbon capture and storage and other renewables. Nukes and CCS have dispatchability and inertia, they have low emissions. In fact, anything we wanted to be built into the NEM, we would hope will have low emissions, very low emissions, not much point in doing it. And cost is, of course, an issue with many of these future technologies. All right, so the approach we're taking tonight is, well, the first thing we need to do is we need to acknowledge that solving this problem in its full complexity is impossible, right? Now, the reason for that is that it's just too big. So Matthew and I have a terrific student at the moment, and he's just modelling the performance of the national electricity market with wind in it. And the wind is uncertain. We're not quite sure how much wind we're going to get from day to day, from hour to hour, or every 5 or 10 minutes. Now, actually just solving the equations for the dispatch of the NEM every 5 minutes for a whole year, with all the equations that the NEM has in it, there's a fair bit of computational effort in doing that. And that's not forgetting, that's just doing it for, the next 12 months. But the decarbonisation challenge is something that we're talking about being decadal in length. So if we're looking at solving the full dynamics of this electricity market as wind blows and the sun shines and the forecasts are right and the forecasts are wrong and gas prices go up and gas prices go down and we have another Prime Minister every 12 months for the next 5 or 35 years, who knows, that just becomes just a computationally intractable problem. And as a result, we need to make some significant simplifications. And the problem is, we always have to simplify something. The problem is to understand when you make a simplification, what that simplification really means and what the limitations to your analysis therefore are. And you have to be really careful about that. And that's where you have to go back and talk to the people who operate the stuff, because I'll say, you forgot about this. And then you realise, oh, yes, I did. And then you've got the wrong answer. So be really careful with simplifying inherently complicated systems. Another thing is, if you wanted to be making pronouncements on what should or shouldn't happen, it's much better to have an argument about the inputs to the modelling. Be very transparent in how you perform the modelling, and then we can discuss whether or not nuclear really is that expensive, or whether or not battery storage is really that cheap, or whether or not wind really is that good or not. Okay? Because we can do scenarios and we can chuck different inputs into our modelling and we'll get different answers. That's just the nature of the beast, as I'll show later on. As a result, we've used all the most authoritative independent sources in our analysis, and that particularly comes for technology costs and future fuel costs from BRE, the Bureau of Resource and Energy Economics, and of course a few publications that have come out of AEMO who make projections of future demand and so on and so forth. All publicly accessible, all well-known documents that nobody would question in terms of credibility. Now, what we're going to do today is we're going to talk about what's the cheapest amount of stuff we can build and decommission in order to get to where we want to get to. And when I say wherever we want to get to, what I mean is wherever the nation, through our elected representatives, decides we want to get to. So we're going to choose a whole bunch of different 2050 targets and look at what sort of results we get. But as engineers, we have a natural tendency to want to just look at how much will it cost in terms of the new build and shutting stuff down as well. Now, the reality is much more complicated than that, of course. When you make an investment on a very large, big piece of kit, you want that thing to be making you money for 30 years, and these investments are lumpy, and there's all these other issues associated with it. Now, it probably is the case in a market of the size of the NEM, lumpiness is possibly not a big issue. Stranded assets perhaps is a different story, but lumpiness itself may not be a big issue. But there are other things, the realities of system operation, different policies, policy uncertainty, markets and governance, our musical chairs up in Canberra, all that stuff. All of those realities of how the world works will then serve, once we've identified the cheapest way to turn stuff off and decommission it and to build new stuff to get to where we want to, the reality is when we actually get there, we'll end up spending more money than that because life's not perfect. But that lower bound, what I'll call the infrastructural lower bound, is still a useful thing to know because that's like the reference to say, well, that's roughly that's the best you can possibly do if you want to get to that point. And then we can define a good abatement policy, and this is how an engineer would think about policy. A good abatement policy is one that results in a plausibly operable system at a targeted abatement for a total cost that is acceptably close to this infrastructural lower bound. So if it's going to cost $100 billion to get from here to 2050 with some set of build, if it ends up costing us 102 billion or 105 billion or maybe even 110 billion, we might say, actually, that wasn't a bad policy. We got to where we wanted to get to environmentally, and we only were 10% over the infrastructural budget, for example, okay? All right, so the problem formulation, we're going to minimise the discounted total cost of electricity generation from 2015 to 2050. And we're going to be subject that to this linear constraint from today of about 170-something megatons per year down to whatever target we, through our elected representatives, choose in 2050. And we're just going to assume for the moment that it's a straight line. And now the modelling that we're going to do has a whole bunch of considerations in it. We're going to include a 10% discount rate. That's what Brear, who we're using as for our technology costs, that's the discount rate they recommend when they're doing their technology assessment. So we'll use that, although we're going to do another case where we don't use that. But we're going to use that in the reference case. We're going to take into account the fact that, as people often say, the wind doesn't always blow and the sun doesn't always shine. So our modelling takes into account the different weather, the wind and solar patterns that we have across the whole NEM, across a whole year. We've taken that into account. We're going to include utility scale energy storage. Energy storage is getting a lot of talk today. You know, you'd have thought there'd been a massive transformation of the electricity system before the first Tesla Powerwall had actually been installed. But energy storage is getting an awful lot of coverage. So let's put one of the cheapest, or perhaps the cheapest form of energy storage in, pumped hydro, at utility scale, and see what benefits it has. Also concentrating solar thermal, you can put energy storage into that in varying forms, so that will appear in our analysis. And then we're going to include also these other plant dynamics. These are part of these technical considerations that we have to take into account. So unit commitment, particularly important for understanding how coal plants function. You can't just turn a coal-fired power station on and off like you can a car. It takes hours to turn a coal-fired power station on, and it takes you hours to turn one off. So when an operator of a large coal-fired power station wants to say, will I generate tomorrow? Yes, all right, keep running. Or won't I? Okay, and they base their judgments on forecasts of conditions the following day. Also, there are minimum on times, once again, particularly important for coal-fired power stations. There's minimum stable generation. A 1 gigawatt power station can't produce 1 kilowatt of electricity. It can go down to, you know, some substantial fraction of its peak capacity. And also this ramping. These huge power stations, be they gas-fired, concentrating solar thermal, coal, nuclear, whatever, there's finite rates at which they can go up and down in their power output, so megawatts per second. So you can't say to a nuclear power station, please go from 50% load to 100% load in the next 5 minutes. It's physically impossible for that plant to do it. So we have to take those things into account. We also have to take into account plausible operational constraints of the NEM itself. This goes back to these quality issues, and particularly this need to account when we have intermittency, that is intermittent renewable plant, wind and solar, pumping into the network and affecting the system loads. And also this, when we have non-inertia bearing plant coming in, that can have impacts on, or can have significant impacts on system operability. So it's a very interesting area when you ask yourself and you look around, and we spent quite a bit of time doing this last year, what network in the world, what isolated network in the world, and that's a key thing, what isolated network in the world has the highest penetration of intermittent renewables into it? It's quite an interesting question. You'll hear some people say, oh, look, Holland's got X% wind or whatever, but it's not an isolated network. Okay, so it's borrowing inertia and also buying and selling energy, but borrowing some of these other things from its neighbours, like France, which is very heavily nuclear. So we're going to be typically conservative engineers, and we're going to say, okay, for this reference case, we're going to relax this constraint later on, but for the reference case, we're going to say you need 30% at any instant in any NEM region coming from synchronous generation sources. Okay? Now that means that could be nukes, it could be coal, it could be gas, it could be concentrating solar thermal, but we're just going to put that in for now. We'll relax it later on and we'll see that it has a dramatic effect. And similarly, we're going to say you can't put more into any region more than 30% intermittent renewables per annum. Now, students of energy here will say, hang on, South Australia's already got that. In fact, it's gone past it. And indeed, you're right. So South Australia, I can't remember the exact numbers, it might be 32, 33% annual energy now is intermittent in South Australia. But a very interesting discussion with a friend of mine from AEMO last week said to me, the Hayward interconnector, the transmission network that joins up Victoria and South Australia last week, was at half capacity because it was down for scheduled maintenance. And what's called the ancillary services market in South Australia then went haywire, and AEMO had to go in and administrate the market in South Australia so the system would keep operating, because there's a lot of intermittent renewables in there and they couldn't borrow inertia from Victoria last week for several days. So we can relax that constraint later on and we'll see what dramatic effect it has, but these physical constraints are real, and last week's dynamics in the NEM is an example of that. All right, so then I'm going to do death by scenario. I've got to try and limit this. I'm only not going to show too many. This is the problem with this sort of stuff. You can end up scenarios on everything. But I want to have this reference scenario, and the reference scenario is what essentially we could do plausibly in the NEM if we're going after deep abatement out to 2050. So we don't have nuclear power generation, we don't have carbon capture and storage, but we got wind, we got solar, we can put in concentrating solar thermal. There's no barrier to that occurring other than its cost, right? But we could do that. Renewables are the only thing that can really do the heavy lifting to get us down to very deep abatement as we currently stand. Now, there are other things that when you look at this modelling, you dig deeper, you realise some of these assumptions, you've got to be careful to not get answers or appreciate when your answers are heavily dependent on your modelling assumptions. The long-lived plant scenario is something I want to talk about briefly. We know that coal-fired power stations last much longer than they were initially commissioned for. Hazelwood Power Station is a living proof of that. I was in the beautiful state of New Jersey last year and out in a boat with kids and my wife last year was a friend of ours who I was collaborating with over there, and he's pointed over there and said, that's Oyster Creek Nuclear Power Station that we were going past in our little boat. He said, that's the oldest operating nuclear power station in the United States. It's a year younger than Hazelwood. Okay, so it's 50 this year. Hazelwood's 51. So, you know, people who operate power stations go in there and change out boilers and change out turbines and rotors and gradually turn the whole thing over and keep it operating. And they find that by running these things for longer and longer and more efficiently and carefully, they actually get these things going for a long time and operating very cheaply. So why can't that happen to a wind farm? We haven't got many 50-year-old wind farms. That's the thing at the moment. But why can't it happen with a wind farm? Or why can't it happen with a utility-scale solar PV power station? I dare say it will happen. The rooftop PV scenario, an interesting one. Many of you here will have rooftop PV on your roof. If you're the most orthodox of finance specialists, you would have rigorously done an internal rate of return calculation prior to your investment. And you would have said, based on a reference debt rate, maybe your mortgage, and based on this careful analysis of my bill, taking into account the metered and network charges and everything else, I get an internal rate of return of this that's plausibly better than the opportunity of cost of investing in something else. So I'm going to put PV on my roof instead of buy shares in something. And that's probably a good thing to do. But I wouldn't have done that calculation. I don't even know how much I pay for electricity in the last quarter. You know, and this is the guy who teaches some of this stuff. And that's just the reality of it. People are putting PV on their roofs because it does give them a bill reduction. How carefully we do that financial investment, well, I can tell you now, I don't do those sort of careful financial investments on anything else, so why would I do it that much differently when it comes to putting PV on my roof? But people are doing it and they're saving money, and actually it is a good investment in many situations. but we're internalising that cost just because we prefer to do that and, I don't know, buy a second electric guitar or something like that. It's a good thing to do. It reduces your electricity bill. You like having it. It's benefiting the planet. Good stuff. And then you're withdrawing some of your electricity demand from the NEM. Okay? Does that affect the prices that we'd see in the NEM? We're going to have a look at that. Then there's this other one, this low discount rate scenario. The Brear report says 10% discount rate, and a lot of people use 10% discount rate, but it's actually quite a high discount rate. Discount rate is basically a weighted average of the money that if you are owning a power station, you would have to give to a bank or a bunch of banks or to equity holders, people who invest in it. Okay? And we all know that interest rates are very low at the moment, so you can get debt cheaply. And we all know that there are a lot of people with a fair bit of money, superannuation funds, for example, who are looking for lower rates of return today than they perhaps were looking at 10 years ago. So requiring a 10% rate of return on a power station today is probably too high, and most studies around the world don't look at that kind of number. Let's put in 5%, and that probably bookends it. A high one, 10%, a low one, 5%. Does that change the answers? And finally, we're going to remove these intermittency and inertia constraints from our system and see what happens to our results. And then we're going to look at the N word and the CCS word. We're going to put nuclear and CCS into the mix and see whether that changes what kind of technologies and what kind of costs we're going to incur. So what do we get? Here's what I'd call a very typical result. So here we have on the y-axis the amount of energy generated each year in the NEM from today out to 2050, and you can see by colour a whole bunch of different kinds of generating plant. Down the bottom here today you see brown coal, here's black coal, so here's Victoria's contribution primarily. Black coal, we have a little bit of wind at the moment here, this is rooftop PV, little bit of gas, and then this is hydro existing up here. And as we go forward to 2050, the first thing we see is demand's going up. We've assumed demand goes up, which is perhaps a brave assumption. It doesn't actually change the prices too much depending on what the demand's going to be, but anyway, we're going to do that. We're sticking with the AEMO forecast on that one, although AEMO doesn't go out to 2050, so we have to acknowledge that uncertainty. But what we see, well, crudely speaking, you see three things happening for this reference scenario, this case without nuclear. We turn out, by 2050, we turn off every coal-fired power station in the country. In this case, we want to achieve 80% abatement of 2000 levels by 2050. And the optimiser, this mathematical thing that's spinning around inside our computers, says, well, the cheapest way to do that is by turning off every coal-fired power station in the country, building a whole lot of wind in the next 10 to 15 years, then as the inertia and intermittency constraints really start to bind, and we haven't got coal because it's got high emissions intensity, we need to start building gas and then concentrating solar thermal so that we can keep getting that inertia and intermittency constraints met whilst the emissions are continuing to drop. And that's, I'd say, a very common result. Various studies have been done over the last 5-10 years, and they get broadly that. Shut down coal, build renewables straight away, and then we have to start building some gas. There's been a bit of a change recently as gas prices have gone up. People would have said, a few years ago, build gas as a transitional fuel rather than renewables. We're finding with our Brear numbers for the gas prices that we're actually having to build gas, and the gas is expensive in this case relative to historical levels, but it's happening later. The first thing we want to do is put in wind. Now, I mentioned before, these sorts of results depend very much on your input assumptions. So one first input assumption I want to change is the 2050 target. So remember, we've got this abatement trajectory, and that one there is 80% abatement by 2050. We could have had 100% abatement. We could have had no constraint. We could have had 20, 40, 60, whatever we want. So how does that 2050 technology mix? We know for 80% abatement, we've got no coal left. We've got lots of wind, we've got lots of gas, we've got lots of concentrating solar thermal. Well, how does that 2050 technology mix change as we vary that 2050 target? So here's our case here that I've already shown you. This is the terminal condition, if you like, of that transition. Unsurprisingly, if we go to 100% abatement, here's our condition here with lots of wind, lots of concentrating solar thermal because we can't be burning gas in a zero emission world. Then if we go back to this case here, which is no emissions constraint at all, look what happens. We don't put in much in the way of renewables or gas at all, and we shut down existing coal plants, the brown and black here, and we build a whole bunch of what's called supercritical black coal plant. And then intermediate results, we see progressively more gas, progressively less coal, and progressively more renewables. So that's the reference case. All right, now, but there's all this other uncertainty. This is discount rates and long-lived plants and all this other stuff. So how do they affect things? Now, as I said, I don't want to kill you by scenarios, so I'm just going to go to the end point. Here's what happens if you've got the same simulation, but now all plants have long life. We've got rooftop PV in there. We're assuming that about, I can't remember, between 10 and 15% of annual generation is coming from rooftop PV by 2050. Now you might say to yourself, that's not a big number, but that's annual generation. That will mean that on a beautiful summer's day where the eastern seaboard hasn't got a cloud in the sky, we're going to be generating almost all of our electricity from rooftop PV in such a scenario, because a PV panel has about a 15% capacity factor across the nation. So multiply its average power output by 7 to give its installed capacity. Okay? So there's actually a lot of PV there. We're going to have a 5% discount rate, and we're going to take off these intermittency constraints. And what do we find? Well, let's look at this 100% abatement scenario to start with. We see lots of wind. Now we see no concentrating solar thermal with storage. The other big renewable is now utility scale PV. And we've already got that rooftop PV, it's not part of the market. And then we've got this pumped hydro kicking in, which is dealing with this intermittent utility PV and wind, so that supply meets demand, even if we don't need to worry about inertia and dispatchability at the moment. But inertia and intermittency constraints. So we see for 100% abatement, by just changing some of these input variables, we get a completely different technological future. It's still renewable because we haven't included nukes or CCS yet, but it's a completely different set of renewable plant, or a largely different set of renewable plant than it is previously. We still get lots of coal when we don't have any emissions constraint, no surprises there, it's cheap, and then we get this transition once again between these two emissions constraints. All right, so is this uncertainty, is this technologically uncertain, is this financially uncertain and other uncertain futures, is it significant? Okay, well the short answer is yes, it is in terms of costs. So here is our estimate of the wholesale market price, what we'd expect to be paying in 2050 for each of these different cases, okay? So this is currently we're paying, 30 to 50 bucks a megawatt hour, and that's primarily coming from coal. Well, let's go back now to this 100% abatement case once again. Here's our reference case, and we're estimating that with that reference mixture of concentrating solar thermal and wind doing the heavy lifting, we're paying 160 bucks a megawatt hour. What about if we make all plants last longer? Well, we save a couple of cents. What about if we change the discount rate from 10% to 5%? We have a dramatic effect. All of a sudden, the price of electricity in 2050 becomes much lower. By the way, these are prices in current dollars for 2050, okay? Then what about if we internalise the cost of solar? And interestingly, there's very little change in the electricity market price. And the reason for that is very simple. We just buy less electricity from the NEM. So we build less stuff because we've internalised that plant inside our homes. So the market price is actually not much different. Then finally, if we remove these constraints around how much the network can handle in terms of synchronous, or in terms of not having synchronous generation intermittency, we once again get a dramatic reduction in price. Now look at this zero emission NEM. We've got a price here in current dollars of 60 bucks a megawatt hour, and here 160. So it's a factor of about 2.5 difference. Now, and similarly you see convergence, but there's substantial market uncertainty in these various options. So it's hard for us to be categorical about what's actually going to cost in any trajectory, because look what happens. A remarkable thing is, look at this number here. This is the best case. This is the best it possibly could be, it seems to me. This number here compared to the reference trajectory if we have no abatement constraint at all. if we don't give a hoot about global warming and keep building stuff because old plants just need replacing, we're saying we're going to be spending a comparable amount of money here than we would be best case for a very low emission network. So it's actually potentially a good news story, but we have to couch that in the inherent uncertainty and the fact that we don't really know whether these systems will really work in these kinds of configurations. So what about nukes and CCS? So we go back to that reference scenario with 10% discount rate and all those constraints, and we put nukes and CCS in. And if you go back to that 2050 zero emission case, you now find that about 2/3 or so of the total generation in a zero emission NEM is now done by nukes. It's not done by renewables, okay? And as you go progressively more aggressive from a coal heavy, see there's this coal heavy world without a constraint, you see nukes becoming more and more significant, and the nukes are forcing out gas plant. Remember, we had lots of gas at 80% abatement, lots of wind. Well, we're seeing much less gas, much less wind, because these nukes, like coal, provide inertia, provide dispatchability, and so compete with the gas on that metric as well. So in fact, you'll see in this case here, when we didn't have nukes, we weren't allowed to have any coal plant built. Now we've got coal and gas in the mix because the nukes allow the coal to exist, okay? So the addition of nuclear generation and CCS once again has a dramatic change on what kind of future we might end up with. Now, a small note there though, is we first didn't believe this when we looked at it, we don't find the CCS penetrating at all, and the reason for that is very simple. The Brear cost inputs that we've used in our analysis say that CCS is more expensive than nuclear. So the CCS, in order to win in this competition, has to beat the nukes and then beat the renewables, and with these cost inputs it doesn't. So, are those costs significant for the big decision of putting nuclear into the Australian national energy market? Nobody's pretending for a minute that's not a massive decision. Well, here's the wholesale electricity price for our reference case, $160 a megawatt hour, and here it is here for $110 a megawatt hour. And you'll see, what's that about? A 5 cent a kilowatt hour reduction off your electricity bill. Is that a lot? Well, depends. What do you think is a lot? What do you think is an acceptable saving for the massive decision of initiating a nuclear power industry in this country? But here's another question, which I think is a more interesting question. If we don't go to a zero emission NEM, because remember, electricity is a third of our emissions, let's say we targeted about 80% abatement in the NEM, right? And we did a lot on transport, we did a lot on buildings, and we did a lot on agriculture at the same time. Then putting nuclear in only would save us about 1 cent a kilowatt hour off our electricity bill, okay? So it has a dramatic effect, what target you choose, as to whether or not you would want to do nuclear in the first place. So, what do we know and what don't we know? And so I'm trying to tie it together now. So the known knowns, paraphrasing a famous politician, the known knowns. The optimal pathways in terms of technology mixes and costs are particularly sensitive to the discount rate and the ability of the NEM to accommodate intermittent renewables. We also know that even if we wanted to, if right now all of us stood up and said, we want nuclear, and we went up and saw Mr. Turnbull and he said, right, let's do it, we're not going to turn on the first nuclear power station much before 2030. It takes the best part of 10 years to build one, right? And it's going to take the best part of probably that time again to have a huge national debate about whether we want to do it in the first place. So whether or not we do want to do it, we're not going to do it much before 2025, 2030. What are the known unknowns? Well, we don't know how much intermittent renewables a large electricity market can really handle, okay? And if you talk to the people who do operate it, you know, that's a substantial concern. That's something that literally keeps some of them awake at night. We also don't know, I mean, my wife will attest, she doesn't know what time I'm getting home tomorrow night today. we don't know what the prices of costs of anything's going to be in 10 or 15 years' time. You'd have laughed at me if I said to you gasoline's going to be half the price that in 2 years' time than it is today. If I'd said that to you 3 years ago, you would have said, what's he on? okay? There's tremendous uncertainty in the cost and price of everything. So, I want to come back to that issue about uncertainty. What do we have in our policy kit at the moment? So it's good to know what we do know, what we don't know, and also what we have. And I want to talk a little bit about the RET towards the end. So there's been a lot of debate on the Renewable Energy Target up to now. It looks like it's survived. The RET looks pretty healthy. The prices are going back up again, and a lot of people's concerns have been allayed. What would the RET look like if we did it out to 2050? It's an interesting question, because we'd say it's a policy we have, and that one and direct action are the only two policies that we currently have, and the RET is one which seems to have been reasonably well embraced by the community. So here's our reference scenario, and this is the proportion of renewable energy that's built in our reference scenario, so gas and everything else, by just constraining the CO2 emissions from now through to 2050. So from now through to 2050, this is the amount of renewable energy the reference scenario says needs to be built in the NEM if we were to achieve 80% absolute abatement by 2050. So then what happens if we say, okay, let's just forget about abatement for a moment. Let's just say renewables. Let's replace that abatement constraint with an 80% renewable energy target. So by 2050, we want 80% of our energy coming from renewables of varying forms, intermittent or otherwise. And then we run the same simulations and we find that for the next 15 or so years, you get the same amount of renewable generation being built in this cheapest way to meet this optimal abatement target, and in this cheapest way to meet a renewable energy target. Now it starts to diverge later on because of these issues of intermittency and inertia and all this stuff I've been going on about tonight. But when we do different targets, 80%, well 100% renewables, unsurprisingly, zero emission NEM and 100% renewables without nukes tells you to do the same thing. But if you do less, you find that for the next 10, 15 years, these two different policies, an absolute abatement policy if you like, and this renewable energy target like policy, gives you much the same renewable energy build and much the same costs. So what that's saying is that not just as a way of stimulating investment in renewables, it's saying that a renewable energy target, however formulated, appears to be close to optimal as an abatement policy for at least another 10 or 15 years, until these real issues of operability start to bite. So, what should we do now? That's really the question. We don't know what we need to do in 2040. What should we do now? We want to do something now which plausibly moves us in the right direction so that we keep making good decisions, keep making electricity as affordable as possible, and continue along a pathway to meet a given environmental objective. Well, the first thing we should do is that we should choose a 2030 target and extend the RET to meet it. The RET currently goes to 2020, let's make it go for longer, okay? And why do we do that? Well, the current RET has broadly functioned as intended. The RET was intended to be a scheme which stimulated investment in renewables. Well, it did that, and it did it at pretty low cost. A small part of our electricity bills has gone towards establishing the RET as we currently know it. An extended RET, from our analysis, then seems to be close to optimal as an abatement policy out to 2030, and it will, as any abatement policy which is close to optimal will continue to put pressure on coal, and interestingly, because gas is quite expensive, it has limited adverse effect on gas in terms of consumer prices. It may not be great if you're a gas-fired power station, but here, as the Australian public, we're interested in minimising our electricity prices to meet a certain environmental goal. At the same time, we need to acknowledge and address the integration of intermittent renewables is a substantial challenge. But the key point is that if a RET-like policy is close to optimal, what that means is it's not the RET that's causing the problem, it's our wish to make electricity as affordable as possible, subject to some environmental objective. So if we put a carbon price on, or direct regulation or anything else, if they're responsible policies, they're going to create the same issues as a RET-like policy will by stimulating investment in intermittent renewables. And we have to work through those complicated issues in a sequential manner. Then at the same time, what are we going to do for post-2030? So that's something we can do to keep going towards 2030. At the same time, we have to plan and implement tangible things to get us beyond 2030. First thing, acknowledge the uncertainty. It's very significant. We have to think about and implement a longer-term abatement target and a broader-based policy. The old broad-based cap and trade scheme, for example. We had a crack at that, wasn't as broad-based as some would have liked. We had a crack at that, we're probably going to have another crack at it. That will then incentivise gas and other non-renewable plant, be it nuclear or otherwise, but things which do provide cost-effective abatement. And then I do think we need to seriously consider the implementation of nuclear and CCS post-2030. But that consideration has to take into account many factors which we haven't done here tonight. Health, security, decommissioning, remediation, insurance, all of these issues which are very significant in terms of nuclear, okay? 6 months in the United States and reading the press taught me that. Now finally, also, the world doesn't sit still. We have to think about the moving reference of a non-nuclear, non-CCS future. In the next 10 or 15 years, we're going to build a lot of renewable plant, hopefully, if we keep achieving abatement at least cost. And as we do that, we'll get better at it. And we might find that as we do it, that it gets harder to justify putting nuclear in the first place. And that's me done. Thank you very much.
Thank you very much, Michael, for a wonderful talk. That gave us really a clear understanding of the issues around electricity generation, depending on the targets that are required for carbon abatement. I'm sure most of the audience will feel much better informed and I hope enabled to participate in what I think is a really important debate that no doubt we and our politicians will be having in the future. So thank you very much again, Michael.